कैसे हो दोस्तों। आज मैं वत्सल आपको बूथ एल्गोरिथम के बारे में समझाने वाला हूँ। हेलो टू ऑल माय फ्रेंड्स। आई My name is Vatsal and today I am going to explain booth algorithm to you all. The content of this video is introduction, implementation, flowchart and an example of booth algorithm. Uh, Booth algorithm is an algorithm which multiplies two signed or unsigned integers into complement. It differs from standard multiplication algorithm, which is implemented and it only multiplies two unsigned integers. This booth algorithm multiplies two signed integers, and it is done using twos complementing both integers. This algorithm uses fewer additions and subtraction uh, than the standard multiplication algorithm. This Booth algorithm was invented by Andrew Donald Booth in 1950. When he was doing his research on crystallography at Birkbeck College in Bloomsbury, London. While doing his research, he needed an technique to multiply two signed integers easily and with fewer additions and subtractions. Now we will see hardware implementation of both algorithm. In both algorithm, there are two signed or unsigned integers. These integers are taken into BR and QR registers. The largest integer of both is taken as BR register, and the smallest integer uh, we- taking out the sign, it is in QR register. Uh, for this booth algorithm, two registers VR and QR are needed, which stores the integer. An accumulator is required. We also need an adder, sequence counter, so that the multiplication takes place only till the number of bits in QR register. The last bit of QR register is taken as Qn, and we also need to do shifting in this booth algorithm and show that another bit is required Qn plus 1. We name this register as A, B, and Q, SE, BR, and QR respectively. Here Qn denotes, as I said earlier, the least significant bit of a QR register. And we also need an extra flip-flop Qn plus 1 for the booth algorithm implementation. Now we will see the flowchart of both algorithm. Firstly, we take the largest number to be multiplied as BR, the multiplicand in BR, and the multiplier in QR. We will convert these both integers into uh, two's complement form. Then we will set accumulator to 0, Qn plus 1 flip-flop to also 0, and sequence counter to number of bits in a number. For example, we multiply 4 and minus 2. As you all know that 4 in 2's complement will be 0, 0, 1, and 0, and minus 2 in 2's complement will be 0, 1, 1, and 1. So we require overall 4 bits. So sequence counter will be 4 for this particular example. Now for the multiplication, we will see the flowchart. We will see the Qn bit and the Qn plus 1 bit. If Qn and Qn plus 1 both are 0 or either 1 1, then we will directly shift accumulator and QR register, and we will decrease sequence counter by minus 1. If Qn and Qn plus 1 is 1 0, then firstly we will subtract BR from accumulator. BR bar plus 1 is equal to minus BR. If Qn and Qn plus 1 is 0, 1, then we will add Br into the accumulator. After this process is completed of either subtracting Br or adding Br, then again we will shift S accumulator and QR register, and we will decrease the sequence counter by 1. We will repeat this process We will repeat this process until the sequence counter becomes 0, and the final value of accumulator and QR register will be in 2's complement together by taking all the bits of AR and QR. We will get our final result of multiplication. And now, friends, we will see an example. We have taken 6 and minus 6 numbers into consideration, and now we will multiply 6 and minus 6. Firstly, we will take BR as 0, 1, 1, 0. It's in 2's complement form, and accumulator AC will be 0, 0, 0. Here, QR is taken as minus 6. And as BR is 0, 1, 1, 0, minus BR will be 1, 0, 1, 0. Now, firstly, initially, accumulator is 0, 0, 0, QR is 1, 0, 1, 0, and sequence counter is 4. So, initialization is done. Now, we will see Qn and Qn plus 1 bits. Here initially Qn plus 1 is 0 and Qn is also 0. So Qn and Qn plus 1 is 0, 0. So for 0, 0, we will shift AC and QR and we will decrease sequence counter by 1. So here we will shift accumulator and QR 0, 1, 0, 1, and sequence counter is decreased by 1. Now this Qn bit is stored in Qn plus 1. So Qn plus 1 becomes 0 and now Qn becomes 1. As this combination 1, 0, we will subtract Br from accumulator. So A equal to A minus Br is done here. So 0, 0, 0 minus 1, 0, 1, 0 becomes 1, 0, 1, 0 and Qr remains the same. After this, we will now do shifting. So shifting of bits takes place. It becomes 1, 1, 0, 1, 0, 0, 1, 0, and we decrease the sequence counter by 1. Now we will see the last bit of LSB of QR, that is 0, and Qn plus 1 becomes this bit 1. Uh, which was the bit of QR, LSB of QR before shifting. Now the combination is 0 and 1. 0 and 1 combination means we have to add BR into accumulator. So after adding BR into accumulator, we get value 0, 0, 1, 0. And after adding, it is shifted uh, by 1 bit. So after shifting, it becomes 0, 0, 0, 1, 1, 0, 1, 1, and this 0 bit is moved into Qn plus 1. Now the combination becomes 1, 0, and for 1, 0, we have to subtract Br. So after subtracting Br in this accumulator, that is doing 0, 0, 1, 0, 0, 1 minus 1, 0, 1, 0, we get 1, 0, 1, 1. Now we will do shifting. After shifting, it becomes 1, 1, 0, 1, 1, 1, 0, 0, and we will decrease the sequence counter by 1. Now the sequence counter is 0, so finally we can end this booth algorithm, and the final answer will be 1101 1100. It's in 2's complement, so now by removing 2's complement, the value becomes 0 0 1 0 0 1 0 0. Its bit is minus and value will be 36. Thank you.